The balance control transformer, or BCT, is a device that claims to reduce electric utility bills by a margin of 6 to 20%. It is presented as a simple transformer constructed without capacitors or integrated circuits, suggesting a potential lifespan of 25 years. The operational principle of the BCT is based on the concept of quadrature. Quadrature refers to a mathematical relationship where two waves are 90 degrees out of phase with each other. In the context of the BCT, these waves are the voltage and current waveforms within an electrical system. When voltage and current waveforms are in quadrature, the power factor ideally approaches zero. This scenario indicates that the electrical power is being utilized for productive work, minimizing energy wastage in the form of heat. The BCT is engineered to establish this quadrature relationship between the voltage and current waveforms. This leads to an improvement in the power factor and a subsequent reduction in electric utility expenses. Evaluations of the BCT in real-world settings have shown encouraging results. In one particular test scenario, a heating application experienced minimal gains, while fluorescent lighting demonstrated significant benefits. The underlying reason is that heating systems typically consume substantial power but may not inherently possess a high power factor. Fluorescent lighting, conversely, generally consumes less power but can exhibit a higher power factor. The BCT has the capability to enhance the power factor of fluorescent lighting systems, resulting in noticeable decreases in electricity bills. While the BCT is a relatively new technology, it holds promise for businesses and consumers aiming to decrease their energy costs. Its simple design facilitates straightforward installation and maintenance, potentially ensuring a long operational life. Individuals seeking methods to lower their electricity expenses may find the BCT a worthwhile option to explore. Consider these additional points concerning the BCT. Firstly, the BCT operates as a passive device, meaning it does not necessitate any external power supply for its function. Secondly, it is important to recognize that the BCT is not a universal solution and its effectiveness varies depending on the specific application. Its efficacy is most pronounced in scenarios where the initial power factor is low. Thirdly, the BCT should not be regarded as a substitute for sound energy management practices. Employing energy responsibly and deactivating lights and appliances when they are not in use remains crucial. When contemplating the installation of a BCT, thorough research and selection of a reputable manufacturer are essential. While several companies offer BCT, the quality and features can differ significantly. Prioritize reading reviews and comparing specifications before making a purchase decision. In summary, the balance control transformer is a device designed to improve power factor by creating a quadrature relationship between voltage and current waveforms. This can lead to reduced energy consumption and lower electricity bills, particularly in applications with fluorescent lighting. However, it is important to consider its limitations and to implement it in conjunction with other energy-saving measures. When evaluating the potential of a BCT, it is helpful to understand some fundamental electrical engineering concepts. Power factor, for example, is a crucial metric. It represents the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. Real power is the power actually used to perform work, while apparent power is the total power supplied to the circuit. A power factor of 1.0 indicates that all of the supplied power is being used effectively. A power factor less than 1.0 indicates that some of the power is being wasted. This wasted power is often referred to as reactive power, and it circulates in the circuit without doing any useful work. Reactive power is typically caused by inductive loads, such as motors and transformers, or capacitive loads, such as capacitors and some types of electronic equipment. The BCT aims to reduce reactive power by correcting the phase difference between voltage and current. By bringing these waveforms closer to alignment, the BCT increases the power factor and reduces the amount of wasted energy. The zigzag transformer configuration, often mentioned in connection with the BCT, is a specific type of transformer winding arrangement. Zigzag transformers are commonly used to mitigate harmonic currents, which are distorted waveforms that can negatively impact the performance of electrical systems. Harmonics can cause overheating, equipment malfunction, and increased energy losses. By incorporating a zigzag transformer design, the BCT may be able to filter out harmonic currents and further improve power quality. The concept of feedback between phases, also sometimes mentioned, involves monitoring the voltage and current in each phase of a three-phase electrical system and using this information to adjust the transformer's operation. This feedback mechanism can help to ensure that the voltage and current are balanced across all three phases, which can improve efficiency and reduce stress on electrical equipment. The claim that the BCT contains no capacitors or integrated circuits is significant because it suggests that the device is relatively simple and robust. Capacitors are components that store electrical energy, and they can be prone to failure over time. Integrated circuits are complex electronic devices that can also be susceptible to damage from voltage surges or temperature fluctuations. By avoiding these components, the BCT may be able to achieve a longer lifespan and greater reliability. However, it is important to note that the absence of capacitors may also limit the BCT ability to correct power factor in certain situations. Capacitors are often used in power factor correction circuits to provide leading reactive power, which can offset the lagging reactive power caused by inductive loads. Without capacitors, the BCT may be less effective at correcting power factor in systems with highly inductive loads. The test results showing that the BCT provided significant benefits for fluorescent lighting but minimal benefits for heating applications are consistent with the principles of power factor correction. Fluorescent lighting systems typically have a lower power factor than heating systems due to the presence of electronic ballasts, which introduce harmonic currents and reactive power. The BCT is able to improve the power factor of fluorescent lighting by filtering out these harmonic currents and reducing the amount of reactive power. Heating systems, on the other hand, typically have a power factor close to 1.0, so there is less room for improvement. The reference to KEMCO, the Korea Energy Management Corporation, suggests that the BCT has received some level of government support and validation. This may provide some assurance of the device's effectiveness and reliability. However, it is important to conduct independent research and to verify any claims made by the manufacturer before making a purchase decision. The assertion that leg-to-leg voltage imbalance is improved is also a potential benefit of the BCT. Voltage imbalance occurs when the voltages in the three phases of a three-phase electrical system are not equal. This can cause motors to overheat and malfunction, and it can also lead to increased energy losses. By balancing the voltages across the three phases, the BCT may be able to improve the performance and efficiency of electrical equipment. In conclusion, the balance control transformer is a device that aims to improve power quality and reduce energy consumption by correcting power factor, filtering harmonic currents, and balancing voltages. While it may offer significant benefits in certain applications, it is important to understand its limitations and to conduct thorough research before investing in this technology. Factors to consider include the power factor of the existing electrical system, the presence of harmonic currents, and the reputation of the manufacturer. Remember that the BCT is not a substitute for good energy management practices. It is important to use energy wisely and to turn off lights and appliances when they are not in use. The BCT is best viewed as a tool that can help to improve energy efficiency, but it should be used in conjunction with other energy-saving measures. To further elaborate on the BCT operation and potential benefits, let's delve deeper into the concepts of power quality and harmonic distortion. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and waveform purity. Ideally, the voltage should be constant and within a specified range. The frequency should be stable at 50 or 60 Hz, and the waveform should be a pure sine wave. Deviations from these ideal conditions can lead to power quality problems, which can negatively impact the performance of electrical equipment. Harmonic distortion is one type of power quality problem. Harmonics are sinusoidal waveforms that are integer multiples of the fundamental frequency. For example, if the fundamental frequency is 60 Hz, the second harmonic would be 120 Hz, the third harmonic would be 180 Hz, and so on. Harmonic currents are generated by nonlinear loads such as electronic ballasts, variable frequency drives, and switching power supplies. These nonlinear loads draw current in a non-sinusoidal manner, which creates harmonic currents that flow back into the electrical system. Harmonic currents can cause a variety of problems, including overheating of transformers and conductors, malfunction of sensitive electronic equipment, and increased energy losses. The BCT, particularly if it incorporates a zigzag transformer design, can help to mitigate harmonic distortion by filtering out harmonic currents. The zigzag transformer winding arrangement provides a low impedance path for harmonic currents to flow, which reduces the amplitude in the electrical system. The effectiveness of the BCT in reducing harmonic distortion will depend on the specific design of the transformer and the characteristics of the harmonic currents in the electrical system. In addition to filtering harmonic currents, the BCT may also be able to improve voltage regulation. Voltage regulation refers to the ability of an electrical system to maintain a stable voltage level under varying load conditions. Poor voltage regulation can cause equipment to malfunction or operate inefficiently. The BCT may be able to improve voltage regulation by providing a stable and balanced voltage supply to the electrical system. This is particularly important in three-phase systems, where voltage imbalance can be a significant problem. The BCT ability to improve voltage regulation will depend on the specific design of the transformer and the characteristics of the electrical system. To fully evaluate the potential benefits of a BCT, it is important to conduct a thorough power quality analysis of the electrical system. This analysis should include measurements of voltage, current, power factor, and harmonic distortion. The results of the analysis can be used to determine whether a BCT is likely to provide a significant improvement in power quality and energy efficiency. It is also important to consider the cost of the BCT and the potential payback period. The payback period is the amount of time it will take for the energy savings from the BCT to offset the initial cost of the device. The payback period will depend on the specific application and the cost of electricity. Before investing in a BCT, it is advisable to consult with a qualified electrical engineer or power quality expert. These professionals can help to assess the electrical system, recommend the appropriate type of BCT, and ensure that the device is properly installed and maintained. They can also provide ongoing monitoring and analysis to verify that the BCT is performing as expected. Furthermore, it is crucial to select a BCT from a reputable manufacturer. Look for manufacturers that have a proven track record of producing high quality and reliable power quality equipment. Check for certifications and compliance with relevant industry standards. Read customer reviews and testimonials to get an idea of the manufacturer's reputation and the performance of their products. By taking these precautions, you can increase the likelihood of achieving the desired results from a BCT and maximizing your energy savings. Finally, remember that the BCT is just one tool in the energy efficiency toolbox. It is important to implement a comprehensive energy management program that includes other measures such as lighting upgrades, insulation improvements, and efficient equipment operation. By combining the BCT with these other measures, you can achieve significant reductions in your energy consumption and lower your utility bills. The effectiveness of a BCT is also influenced by the overall design and condition of the electrical distribution system. Factors such as wiring size, grounding, and overcurrent protection can all impact the performance of the BCT. It's also important to consider the specific types of loads connected to the system. Some loads, such as variable frequency drives or electronic ballasts, are more likely to generate harmonics and benefit from power quality improvement measures. Other loads, such as resistive heaters, may have a near-unity power factor and not benefit as much from power factor correction. To maximize the benefits of a BCT, it's important to ensure that the electrical distribution system is properly designed and maintained, and that the types of loads connected to the system are compatible with power factor correction. A proper understanding of these factors can help to ensure that the BCT is installed and used effectively. Also, remember to consider local utility regulations and incentives. Some utilities offer rebates or other incentives for installing power quality improvement equipment. These incentives can help to reduce the upfront cost of the BCT and improve the payback period. It's important to research available incentives and to factor them into the overall cost-benefit analysis. Finally, keep in mind that the performance of a BCT can degrade over time due to factors such as aging and environmental conditions. It's important to establish a regular maintenance schedule to ensure that the BCT continues to operate at peak efficiency. Maintenance activities may include visual inspections, cleaning, and electrical testing. Regular maintenance can help to prolong the life of the BCT and maintain its performance over time. In summary, the balance control transformer can be a valuable tool for improving power quality and reducing energy consumption, but it's important to consider all of the relevant factors before investing in this technology. A thorough understanding of power quality concepts, electrical distribution systems, and load characteristics is essential for maximizing the benefits of a BCT. It's also important to select a reputable manufacturer, consider local utility regulations, and establish a regular maintenance schedule. By taking these steps, you can increase the likelihood of achieving the desired results from a BCT and realizing significant energy savings. Also, if the transformer is installed outside, protecting it from the elements can prolong its life. Also ensure that proper ventilation is available for the BCT to prevent overheating.